Good afternoon, everyone. In the today's session of this MCMT, we'll be discussing regarding the work conditions of the tool upon machining process and the tool life based on the behavior of the concerned material which is being utilized in the working process as a tool. Due to the induced stresses during the machining process, what are the precautionary steps need to be taken for increasing the tool sustenance? Or generally we will be calling the incrementing of resistance for the tool. We need to commence the different kinds of processes by the tool. Coming to the basic definition related to the tool work. So we all aware of the work as a mechanical property that is done due to the repetition of loads that are being induced on the material or on an object. For our better understanding, gradually I am taking one of the pen cap and there will be a slide holding device towards it. I'm continuously applying some of the load to enhance that particular holder. So obviously, if repeatedly I have done so, automatically it will be changing in its stress strain behavior. So that's I'm telling that the behavior of the material. So upon inducing of the repeated loads over the material, it leads to the strain that resists only to a particular limitation of the timings, and if beyond the hook slide has been attended, it crosses the elasticity limit, plasticity will be entering and directly to the maximum upper yielding point of view and tends to the rupture of the material, that the holder will be getting detached from the pen. It's a minimum example that upon repetition of the loads, the behavior of the material will be tends to the fracture of rupture directly to the maximum yielding point state directly from the proportionality limit to the upper yielding point or high or maximum tensile load conditions, we can say in our mechanical strategy. Now coming to the basic definition of this tool work, it's a gradual failure. So see here the term gradual initiates that repetition of the force is being impacting the failure condition. So it leads to the repetition of the strains. So one force is applied and repeatedly the same force is applying on the same material. It leads to a deterioration or deformation of the material internally, but suddenly it leads to a gradual change that leads to a fracture condition or a rupture point by maintaining an upper yielding point or ultimate tensile load conditions. The gradual failure of the cutting tools due to the regular operations is known as the tool wear. Hence, what are the different types of modes of cutting? Tool failures or fracture failures will be occurring. The mode of failure occurs due to the mechanical breakage because of the heavy forces that are acting at the tool point, which leads to fail suddenly because of the brittle fracture. See here, the similar load which is applied repeatedly, in the sense, considering our lathe machine, which is holding the object which need to be machined for better dimensions achievement, and MRR process material removal has to be considered over the material with the help of this tool. So the coefficient of friction will be getting developed. The rotation of this spindle will be considered per minute. Based on the rotations, the feed and depth of cut will be induced by the tool over the material. So this is a repetition, continuous process that is being acting on the material for eliminating the excess material in the form of a chips or amorphous state or tiny particles, which will be having an irregular shapes. So due to those forces, if at all any of the excess feed rate has been given to the machinery device, then automatically either of the dimensions deviations will be occurred in the workpiece, or else high stresses will be produced towards the tool. So leads to a failure condition, and that to a brittle fracture. That is also known as a mechanical chipping. This kind of tool failure is very much random and within the general processing conditions, either of the lathe machine conditions, milling machine conditions, drilling machine, that results a premature loss of the tool. Hence, you cannot determine also even in the experimentational process commencement. So unknowingly, the continuous loads are being acting over it. Continuous cutting parameters such as speed, feed, and depth of cut are also executing over the devices, indeed to achieve the better accuracies regarding it. But ultimately, it leads to an extremely detrimental conditions, the loss or failure of this tool. And this will be happening because of the different conditions. Either the development of the high frictional forces, hence it leads to an high thermal stresses producing at the mating condition of the tool and the work part. So because of those stresses, thermal stresses, normally it has been termed as temperature failure. Thermal stresses that will be produced due to the frictional forces acting or friction that is developed between the tool and the work part. So those are also known as this temperature failure because of the elevation of those temperatures at an extreme conditions. So beyond the limitations is called extreme conditions. So those are called as temperature failure. So due to those stresses development internally within the tool, when the process commencing, the failure occurred over it is the temperature failure. And this causes the tool point to soften, that which leads to a plastic deformation that completely changes its dimensions other than the recrystallization level, and the sharp edges will be getting lost. And even this failure occurs in rapidly also, that results a loss of tool. Generally we'll be calling the tool has been broken, tool has been lost, That's the tip. Have to go for sawing it and getting the original shape out for the existing HSS material like that. And even this is quite detrimental and unwanted also. And both the kinds, that is, failure need to be prevented by using a suitable materials, that is something about the replacing of the tool over the similar kind of materials by maintaining the geometry, similar geometry. That the geometry also will be regarding the work part. Regarding the work part also, the geometrical specifications are directly proportional to the tool monitoring over the specimen. Hence, this geometry depending upon the work material and even the cutting conditions, or is what we are calling the cutting parameters. Cutting parameters in the sense speed, feed rate, and the depth of cut. Nextly, the gradual work conditions. So we all aware of this work condition. Due to the repeated loads, the stresses will be produced within the material, leads to the deformation conditions to an elasticity of range by maintaining the high ultimate tensile load conditions. That is nothing but the gradual wear of the cutting edge, which is causing the loss of tool shape and even reducing the efficiency of the cutting parameters. Finally, the internally produced stresses upon repeated kind of loading leads to an maximum shear conditioning levels by the elevating of high temperatures other than the existing limitations by the elevation of these frictional forces at the surface of the material and the interaction of this tool tip and the material leads to an high thermal stresses inducement will be nominally used to call this thermal failure or temperature failure. The tool work. So where the work condition will be taking place and whether it is passing throughout the material or else a minute level, it is limiting to a particular minute level. We'll be having a detailed discussion towards it. Look at the pictorial representation that is displaying on the screen. The entire part of this is the cutting tool. Nominally, will be having the in the square shape itself, which is of the HSS material, high speed steel, and the tip will be grinded on our grinding machinery, which is having with respect to the cork or graphite material. And will be forming the cutting edges in the form of then a V with an sharp edges or sharp tips achievement, which will be normally calling as a flank work or flank surface, which will be utilized in here, U-shaped or V-shaped or wedge shape. So the required shapes based upon the cutting process will be getting the shape by utilizing this grinding machine. Coming to the gradual wear. So gradual, it's a point or synonym used to refer towards that slowly it will be coming into the deformative condition that changes its dimensions from the normal conditions to the maximum plasticity range of conditions. Basically, this gradual work occurs at three principal locations. First one is the cutting tool, work conditions, occurrence. Secondly, the cutting tool, flank work conditions, occurrence. Thirdly, the corner wears at the cutting tools. See here. This is a mating point or intersectionary point of the two different edges occurrence here. So hence, this is the corner that will be having or the tip of the material nominally. So if this tip has got in contact with respect to the work part, which is machining or the consent process for MRR condition. So at that place, the tool or the tip of the tool will be directly interacting with respect to the work part and leads to an shear conditions over there. So continuously, it should be in contact with respect to the material for removing the excess material existing of the workpiece in order to achieve the required dimensional accuracies. And secondly, at the flank work. So this is the flank work resistance. Sorry, a flank work, which is utilized for a major cutting edge, which is a nominally we'll be calling as a major cutting edge, which will give the perfect dimensions over the surface finishing or the work parts, because this will be having the sharp edges from the cutting worm even after a particular time period, by elevating a minute or micro level of deformation with respect to the slant angle of the tool bit. Coming to the crater wear conditions, a minimal amount of material will be getting to the deformation in a majority strategy, where that particular chip contact area is being accessed directly with respect to the tool. Nominally, it is displayed here, the crater where the material, the chip material, which the material is being detached from the parental workpiece. At that particular zone, only the high thermal stresses will be produced, as we have been discussed in the previous slide. A work condition. See, this is an edge condition. Nominally has displayed here. This is the crater work. So this is the crater work condition happening nominally at the one surface area, that too from the one edge side direction. It consists of a cavity or a concave section of the tool that is facing or to the tool face, which will be forming some of the grooves over the action of the chip at the surface of the work part. Nominally, at that particular level, high stresses and high temperature stresses, shear stresses, normal stresses will be getting produced due to the interaction of this tool over the work part. Coming to the characterization of the tool, listen, at the chip contact interface, which is contributing towards the work condition. See, nominally, where this particular edge is getting in contact for the machining process for the MRR condition, this tool should be in characterize or in contact with respect to the work part. Nominally, it leads to the inducement of the stresses, nominally generating towards the frictional forces, which leads to a maximum range, and depending upon the coefficient of friction or frictional levels, high thermal stresses will be induced at the meeting point, leads to a maximum deterioration condition over the work part for achieving the better dimensions over the work part, and a minute losses of the material over the tool tips which has been directly in contact with respect to the work parts. That's the work conditions, slight work conditions. Thus, that crater can be measured either by the depth or its area of identification. And even this crater affects the mechanics of the process or the mechanism of the process. It leads to an incrementing of the cutting angle that usually deteriorates the dimensions deviation over the work parts. Even at the same time, this crater leads to the downfall of the mechanical properties towards the strength activity, strength and stiffness. So automatically when the strength or stiffness towards the material has been decreasing from point to point or with respect to a particular time, due to the machining parameters such as speed, feed and depth of cut, if the speed of the machinery is being maintaining, even though it is maintaining at the same RPM, due to the decreasing in its strength, automatically it leads to an predominance, wear predominance condition, and leads to an permanent loss of the tool. Generally, it is caused due to the friction at the interaction between the tool and the chip, and even because of this build-up edges, which creates the large dimension status that relates in a bulging like situations, that leads to a large irregular dimensions of chip elevation over the surface of the material at the machining process when the tool has got interacted with respect to the surface of the machining work part. And even this is caused due to the abrasion action of the microchips which are present at the chip and tool interface point also. So it leads towards the damage of the properties which are existing within the material, tool material. And even the diffusion wars are occurred due to the atomic attraction between this tool and the work part atoms or the tool material. Normally, it will be getting diffused and deposited over the workpiece, which will be generally calling as under this diffusion of the work. Due to this agitation, also crater wear will be getting produced. Coming to the flank wear. So flank wear. See the wedge condition which is maintaining by the tool. This is the tool, and this is the tip of the tool, which is getting slided over the workpiece, and workpiece will be moving towards the right side direction, and tool will be existing in the similar position with respect to maintaining a pointal cuttings or else the oblique cutting by maintaining a inclination with respect to the surface. Coming to this flank work, It will be occurring due to the friction between this machined surface of the workpiece and the tool frank at the edge where the tool is getting interacted with respect to the surface of the material. This flank appears in a burr land, and even it is measured in the VB, nominally called as the burr land, which affects a great extent towards the mechanics of cutting. And moreover, at this point of cutting, the surface cracks will be maintained and it even passes through the subsurface levels of the material in the form of a notches. Hence, that is called a notch work. So it is the condition that will be arrived or achieved because the work surface will be very much hard and abrasive than the internal layer material or the same material, which is caused by the work hardening during the machining process. The burr predominates at a low speed due to the following acetations because of presence of the friction at the tool work interface, the abrasion action of these microchips present at the tool work interface and causes the diffusion work condition during the machining process. Normally, this diffusion was due to the atomic attraction between this tool and the work material will get diffused and those will be getting deposited as a layer over the workpiece. Nominally, for best example, when the ferrous content of material has been reacted with respect to the water or hydrodized or oxidized, a layer of this rusting will be getting formed. In such a way, a thin material that will be getting deposited over the workpiece that is called as a diffusion work. In our general language, we'll be calling it a slight crack that has been occurred at the tip of the or edge of the tool. See, normally this is the work part containing the step cutting in the lathe machine process, removing a excess material. So this is the original dimension, and this is the dimension need to be achieved. This is the dimension need to be achieved, and the excess material need to be removed by considering a feed rate by the tool, interaction of the tool, and this is the tool, sharp cutting tool. The sharp edge will be coming into the contact, and this is the wedge shape, and the corner will be elevating the chips towards the removal of the removal from the work part. Because of this precision of the machining, the material in the form of a chips will be getting removed upon machining condition. The corner burr condition is actually shortens the cutting tool at this particular level. The corner point at the tip of the tool will be calling generally. It shortens the cutting tool and leads to an increasing in its dimension of machined surface, and it leads to an dimensional error in the cutting area. See, nominally used to chatter in normal conditions, and cornel width is reduced due to the tool length because of the material will be getting lost over the frictional forces development, and because of that work conditions maintaining over the corner or nose, or generally we'll be calling as a tip of the tools, obviously leads to an errors causing in the dimensions of the material. But one thing it is confided, we can conclude in a positive way that additional amount of material all has to be removed from the work part itself. But additionally, chips will not be getting elevated. So minuting in the form of this MRR process with a slight error. So nominally, if so has been happened, these conditions has been developed in the machining processes. The dimensions will be having a bit incrementing as the error identifies during the machining process. See, nominally, the error which is causing about the value of 0.03 to 0.05. So if the exact precision need to be maintained after the cutting process is, for example, 2 mm, but an additional amount of this surface finishing will be existing towards this 0.03 to 0.05. Nothing but if I need after machining only this as an 2 or 20 mm in the diameter, but it will be having 20.05. So that's in a positive aspect that repeatedly one more working methodology can be progressed and we can attain the material to the required dimensional accuracies. But if at all the feed rates has been increased or depth of cut has been increased, that leads to the formation of this corner wear or nose wear at that particular situations. A rough surface finishing will be achieved and leads to an high MRR process. Coming to the point of this tool wear mechanisms, how, what is the wear condition and where it will be occurring nominally. First one, due to the abrasion, the tool wear will be taking place. Tool wear mechanism, abrasion. This is an mechanical wear caused by the hard particles in the working material, removing the small portions of the tool or the small portions of the tool. Because even we have been discussed in the previous session also that materials, working on different kinds of materials, classified into metals and the non-metals, further classified into the ferrous content of metals and non-ferrous content of metals, polymers and ceramics in the case of this non-metals. Let's have a detailed deviation between this ferrous content and non-ferrous content. So by maintaining the less parameters regarding this non-ferrous content of materials can be machined very much fastly by the less stresses inducement and can have the better efficiency over it. In order to machine over this ferrous content of materials, it's a little bit heaviest process that the materials in the case of this ferrous also having the heavy strength one compared to the non-metals. Hence, this will results in the deviation or removal of a small portions over the tool also. That particular abrasion, that is called abrasion, and that will be getting elevated from the tool in the form of a amorphous state. There's a light powder state, and at that particular region, both the flank wear and crater well will be coming in the picture, and this leads to a cause of this flank wear. That's due to the abrasion. Coming to the adhesion concept. When two metals are forced into contact under a high pressure and temperature, nominally we will be looking after over the welding processes, adhesion welding process. At that particular time, this adhesion takes place with a high pressure and temperature. Nominally, these conditions in our working processes, MRR condition process also will be taking place between the tool surface finishing, tool tip and the surface finishing of the object, which need to be machined. As this chips flows across the tools, small particles of the tool are also will be broken away from the surface, from the tool surface. So the majority of the material will be removed from the work part, but the minute strategy, that is 1/100th position of the material will leads to the work conditions regarding the surface of the tool that results in the attrition of the surface. Actually, coming to the point of this diffusion, it's the process of exchanging the atoms and take place across the close contact boundary conditions between the two different materials or similar kind of materials. Nominally, it occurs at the tool and chip boundary, leads to an depleted status, and nominally it increases the hardness at the surface point of view. So nominally, if this condition is progressing simultaneously, this development of this hardness relates to the abrasion and the adhesion towards the cutting process. That is nothing but high interaction with respect to the thermal stresses produced over it, nothing but temperature stresses, and even leads to a high frictional forces development. This leads to a mechanism of the crater rupture. And another one parameter that is chemical reactions. At these high temperatures and even the clean surfaces, nothing but the level of this tool and chip interface due to the machining process. Because of these high speeds that we are commencing at the machining processes, it leads to soften the parental materials and results in the case of this chemical reactions, particularly oxidation process will be taking place at the rack phase of the tool, which leads to a softening of the material and gets the shearing conditions, and is related towards the exposing of the new material to sustain the reaction process. Coming to the plastic deformation, the cutting forces which are acting on the cutting edge leads to a high temperature stresses involvement, which leads to deform the edges plastically at a plasticity of range. Mainly contributes this flank wear. Nominally, this is the curve representation of the tool wear condition with respect to the cutting parameter or the x-axis and tool flank work occurrence during the machining process. Nominally, the normal initial work conditions will be produced after the sustenance limitations, and if at all the same steady state will be getting progressed up to the uniform work conditions has been maintained during the time of cutting. If at all the maximum strains has been produced within the material utilized as a tool that crosses the limit of the steady state work region, it leads to an producing of high temperature at the interaction point of this both tool and the work part. That automatically takes to a maximum tensile load conditions, proceeds for the permanent failures due to the repeated loads over it. Nominally, in the display, it is being clearly specified that firstly the break-in period where the sharp cutting edges were rapidly utilizing in the machinery working process for about a particular time period, and next steady state period is being entering because of inducement of the repeated loads over the work tool. So gradually the strains are being increasing to a particular level, and if at all the high frictional forces or temperature or thermal stresses has been produced over it, directly the plasticity of range, nothing but permanent failures of the tool will be coming into the conditions. And before that, the accelerating work condition is being taken place to a minimal void, that is a failure region as specified in the diagram. Later on to a rupture point, it leads to a final failure. So different conditions during the machining process, the flank work conditions, and depending upon these conditions and the type of materials which are utilizing as a work part, we can analyze the tool life and its behavior. So regarding the tool life, we'll be discussing how we need to increase the tool life. We'll be discussing in the next class. Thank you.